Alright, in this video here, we'll be talking about the rest of Chapter 2. So this is Chapter 2, Part 2. We're going to be at 2.3, which is talking about other types of graphs. We have bar graphs, pair 2 charts, time series graphs, pie graphs, and dot plots. We'll start off with our bar graphs. It's simply a graph that represents data by using vertical or horizontal bars. With heights or lengths representing the frequencies of whatever you're analyzing. The steps to drawing a bar graph is simply to, like all graphs, label the X and Y axis so that one represents the group or class that you're analyzing and the other represents the frequency. Then step 2, simply draw the bars that corresponds to how large the frequency was for those groups or classes. So in example 7, we're going to look at sales for fast food franchises. The data gives the worldwide sales in billions of dollars for fast food franchises for a specific year. So we see that Wendy's has 8.7 billion, KFC has 14.2 billion, Pizza Hut is 9.3 billion, and Burger King is $12.7 billion. And then Subway is $10 billion. Again, this comes from the Franchise Times. So if you are wanting to make a bar chart, either horizontal or vertical, you would have them as such. So again, you can see that the X and Y axis is labeled, so you can see what the companies, which is what we're looking at, the billions of dollars, that happens to be our frequency in this situation. So you see companies, billions of dollars, and then the bar charts, you can see depending on really what I want you to focus on here. This right here looks dramatic because they're starting at 8 billion and going up to 16 billion and going up by twos. So Wendy's and Pizza Hut definitely looks a lot less than KFC and Burger King versus this horizontal bar graph. You can see that because they started from 0 and went to 15, went by 5, so it's still an equal chart. It's just not as dramatic. So what this does is, again, when we have a skewed bias data, we're always in statistics, we're always trying to convince people that we're right. Using facts, we just skew how the charts looks, how the graphs look. It's all true data, but we have to keep an eye on things like this, right? Where we skip to 8 instead of starting at 0. There's nothing wrong with that. The data is still true. We just got to analyze it correctly. So do watch out for that when you're looking at things on the news and stuff like that. A pair 2 chart is a special version of a bar graph that represents the frequency distribution for a categorical variable. The frequencies are displayed by heights of vertical bars arranged from largest to smallest. All right, so again, a pair 2 chart is very similar to a bar graph, but it is organized from largest to smallest. That would be the difference there. So let's look at an example of that. So in example 8, we want to construct a pair 2 chart. To create a pair 2 chart, we're going to again use vertical bars and put the categories in order from the highest frequency to the lowest frequency. Again, we'll use our vertical bars and we're going to make the bars the same width. Don't want one bigger than the other, always the same amount of distance on your frequency axis. Again, arrange the data from largest to smallest by frequency. Units used for the frequency scale must be of equal size. Again, very important. And then we're going to construct a chart for the worldwide sales that we just saw in example 7. And we're going to include the categories labeled and the scale for the frequencies. So let's do that here. So I feel like my chart, I'm actually going to see if I can't get it to be one page. It is not going to let me. All right, worst case scenario, we'll open up a new document like last time. All right, here is our chart on one page. So what we're going to do is, again, just label your information. So I'm going to go with companies. Let me pull up the data so I don't got to keep going back and forth. All right, so we had, where did it go? Hold on. Here we go. All right, so we had Wendy's, KFC, Pizza Hut, Burger King, and Subway. Again, we want to go from largest to smallest, so I can see that my largest one would be KFC. So I'm going to let this be KFC. I see that my next largest one is Burger King. I'm just going to say BK for Burger King. I see that the next one is Subway, so I'll do SW for Subway. Followed by Pizza Hut, so PH. And then Wendy's coming up at the end. I'll just do a W for that. You can spell it out if you would like, but it doesn't really matter. Again, I'm going to go the chart. This part here on the frequency is again going to be the money in billions. And I'm going to actually start at 0, and I'm going to go 5, 10, 15. I believe that would be it. And then 20 if I needed it. But I think 14.2 is the largest. So KFC is at 14.2. So if this is 15, we're roughly about right here. All right. Try to make that about the same depth as you can. Burger King is at 10. But nope, Burger King's at 12.7. So that's about halfway. Subway is at 10. Pizza Hut comes at 9.3. And then Wendy's is at 8.7. So this is 9.3, 8.7. This would be 7.5, about 8.7, probably about right there, give or take. All right, there you go. So that is a pair 2 graph. So same thing as your bar graphs, but again, notice this time it went from largest to smallest and not just the order of the data that we got. All righty. The next graph we're going to look at is called a time series graph. And it's just a graph that represents data that occurs over a specific period of time, hence the name time series. Just like, again, like all other graphs, the very first step, draw and label your X and Y axis. Step 2, label the X axis for your years and the Y axis for the variable over time, whatever your categorical information you're looking at. Step 3, plot each point according to the table that's provided. Then step 4, draw the line segments, not curves, connecting adjacent points. So you'll see that a time series graph is a lot like a line graph, but for time specific. And so let's look at something that for an example there. So in example 9, we are going to look at the percent of cigarette smokers. The data shows the percentage of U.S. adults who smoke, and we're going to draw and analyze a time series graph of data from starting from 1970 all the way to 2010. So you can see in 1970, I have my categorical data. That would be the years. Then I have my frequency. In this case, it's a percentage. I have a title. And then the way they do this is, again, in 1970, there's about 37%, which is located right here. 1980 goes to about 33%, so that's located here. 1990 is about 25%. 2000 was 23%, and 2010 was 19%. So they plotted all of their points and then connected them with a linear line, not curves, but a straight line. So it is very similar to a line graph, but over a specific time. This was years. It doesn't have to be years. We could always do graphs for minutes, hours, seconds, depending on how drastic our data is changing. Maybe we want to see the height of a plant growing. We would probably want to go by days in that example. So again, it does not limit to years. Just in this situation, it was. And then from that data, you can then conclude some things. Again, draw conclusions off of facts. Doesn't mean you're right. It's just a conclusion that you are drawing. So we could say there has been a decrease in the percentage of U.S. adults who smoke over a 40-year period. That's what we can pull from this data. Your argument could be, well, that might be true, but then there's now an uptick in cigarettes or vapes or whatever you call those things. And then that could be the reason why there's a downtick on cigarette usage. But you can draw all kinds of different conclusions from the data, just depending on what point of view are you trying to get your audience to see. All right, let's look at a different example. We'll look at example 10, and then we'll see amount spent on Valentine's Day. So again, the data shows the average amount of money spent by consumers on Valentine's Day. We have years from 2007 all the way to 2012 and the amount of money each year. So again, we're going to draw a time series graph for the data and comment on any trends that we might see. So again, you want to do your years. So I'm going to have 2007, 2008, 2009, 2000, oop, that's not a 2, 2010, 2011, and 2012. Now over here for my measurements, I think I'm going to go by 20s. I'm going to go 20, 40, 80, 100, 120, 140, 126 is the largest. I could have probably spaced that out a little bit more, so let me kind of redraw those to space it out. So we'll go 20, 40, this might be too much of spacing, 80, that'd be good. So 100, 120, and then 140. All right, so now that I have a decent amount of good spacing, good little trend, basically in the sense that they're the same width. So 20 to 40, 40 to 80, 80 to 100, 120. To make sure that's the same, you can't go from like 20, then 30, then 31, then 32. It has to be the same distance. All right, so in 2007, the average amount spent was $120. So we'll put a dot right here. In 2008, it was $123, so slightly above that one. In 2009, it went down to $103. 2010, same concept. 2011, $110, so about halfway up. And then 2012, we went all the way up to about 126. So we plotted all of our points, and now we're going to make lines, not curves. There you go. So that would be your time series graph over the years of 2007 to 2012. And it says now we're going to draw a comment on a trend or draw a conclusion. And then you can draw any kind of conclusions if you would like. We can see that you can conclude after 2008, the amount of money spent on Valentine's decreased until about 2010. Then you saw an up increase. You could draw a conclusion on why. Maybe there was just more stress. I want to say in 2008 was a stock market crash, I believe. And so maybe they just didn't have that kind of money to spend on their Valentine's Day. But again, you're just drawing conclusions on things that you might know versus what you are seeing. But the biggest trend that you can say is that the trend decreased after 2008. And then started to increase after 2010. You could also say in there that it plateaued from 2009 to 2010, drawing a trend from what you see and then maybe adding a little more to it, depending on what you're trying to prove. All right, the next type is called a pie chart. And it's basically, again, a circle that is divided into sections or wedges according to the proportion of frequencies. In each category of the distribution. So the first thing we're going to do is we're going to divide the frequency for each class to a proportional part of the circle. The degrees will just be the frequency divided by how many. So the total in your observation, maybe there's 20 people you're observing, whatever the situation might be, times 360. So all of them should add up to 360 at the end. But again, F is your frequency, N is the sum of the frequencies. So like if you had 20, maybe this frequency only happened twice. So it'd be 2 out of 20, and then you would multiply that by 360. Then step 2, we're then going to convert each frequency to a percentage. So you again take that exact same situation, frequency divided by the total number times 100, and now you have a percentage. The third step using a protractor and compass, we're going to draw the graph with angle measuring the degree values found in step 1 and label each section with the class name and percentages. Just an FYI, you'll be using like technology to produce that. And really, it's just the numbers I care about. Like, do you have the correct degrees and percentages? Like the chart below. So let's look into that so you can kind of have an idea of how you'll analyze this. So in example 11, reasons we travel. So we're going to use the data to determine the degrees and percentages needed to construct a pie graph for reasons we travel data. And then we're going to construct a pie chart off of that data. We're not going to be using a compass and a protractor, but we're going to make sure the wedges are proportional. So for instance, if you can see this, the purposes of the reasons we travel are personal, business, visit friends or relatives, work related, or leisure. You can see that leisure has the highest frequency, so it better be the largest wedge. I'm not going to calculate it using a compass to make sure it has the correct degree, But when you are drawing it out, I would want to see that that one has the biggest wedge, and visit friends or relatives has the smaller wedge. But again, what I'm going to be specifically looking at is, do you have the right degrees and percentages? So again, to get the degrees, you're going to take the frequency, which in this case is 146, divide it by the total. So we need to add these up. So let's pull up a calculator. In this case, that's going to be 146 plus 130 plus 225 plus 299. Let me see sure I got that. All right, and that gives us a grand total of 800. Let me put this away. So I get 146 out of 800, and then I would multiply it by 360 to get my degrees. I'm getting a little bit of a lag. Give me 1 second. There we go. All right, so that should fix it. Much better. All right, and then the percentages, same concept. It'd be 146 divided by 800, but this time now times 100. And so then you can kind of write out all of your correct procedures. And just so you know, this total should be 360. And then this total should add up to 100. You might be plus or minus 1 point off, adjust as you need. Could just be a rounding thing. All right, so let's pull back that calculator. I'll make sure we got plenty of room. All right, so we're going to do 146 times 800. Oh, my bad. Nope. 146 divided by 800, and then multiply that by 360. So I can see my personal business should be 65.7 degrees. Not going to take off if you don't put a degree sign. The next one is 100 and so we have 130 divided by 800 times 360. So my visits with friends and relatives should be 58.5 degrees. My work related, so that'd be 225 divided by 800 times 360, should be about 101.25 degrees. And then our last one, our leisure, so that's 299 divided by 800 times 360, and I get 134.55. And then you would just check to verify that that does give you 300. So I'm going to take, or 360. So I'll take that number and I would say 134.55 plus 101.25 plus 58.5 plus 65.7, and I get 360 degrees. So I know I got my degrees right. Now I can do the same math for my percentages. So that's going to be 146 divided by 800 times 100. So now my personal business is actually 18.25%. Again, not going to take off if you don't put a little percent sign. The title is right there, so we're good with that. 130 divided by 800 times 100. And we see that visit friends or relatives was 16.25%. 225 divided by 800 times 100. And I can see that work related is 28.125. And then 299 divided by 800 times 100. I can see that that was, so again, leisure was 37.375%. And of course, we just want to make sure our numbers are correct. So we're going to add that to 28.125 plus 16.25 plus 18.25. And we get 100%. Right? Now, with that data, you then are able then to produce a pie chart. All right, so I'm going to see if I can keep that data right there relatively. So here we go. I put it like right below it. That's what I need. There you go. Okay, so there's my pie chart. You do your best circle, and then you just kind of want to make your wedges. If I know this is 360, I know half is 180. Remember my largest degrees. I think I forgot my one here. Should be 134. So it's not quite a full one, but I know this is 90. And if I did half of that, that'd be 35 on 190. I mean, 45 on 90, so that's 135. So that is kind of how I'm going to design this. I know this would be 90. Half of a 90 would give me about 135. So I would say roughly this right here would be my leisure at 37.375%. All right, then looking at the next one, 101. Again, I know that this is 90. So if it's 11 more than that, we're probably looking at about maybe like something like this, where that was work related. At 28.125%. All right, my next ones are about 58 and 60, so they're almost about the same. So here's about the halfway mark. I'm just going to make one slightly bigger than the other. The one that's slightly bigger will represent my personal business. Leaving the last section as visit friends. I know it says and relatives, but that's about all the room I got for that one. So this again would be at 18.25%, and this would be 16.25%. Right? And so there you go. So you would have your breakdown of your percentage. So someone can look at this pie chart and go, all right, we can definitely see majority did leisure. I can see specifically it was 37%. I can see visit friends was the smallest at about 16%. And that's really what they're trying to just catch. Now, you could have the percentages there, but if your wedges are not proportional to what your percentage is saying, it might skew the data because they might go, like for instance, if a visit for friends I had 40% and leisures was at 37, I'm still going to think, well, leisure is more because of the way the wedge of the pie chart is versus what numbers you actually have up there. So again, make sure that the wedges of a pie chart are proportional, but I am not going to get a compass and a protractor and measure that out. All right, the next one is called a dot plot. So a dot plot is a statistical graph in which each data value is plotted as a point or dot above the horizontal axis. So in step one, we'll find the lowest and highest data values and decide what scale to use on the horizontal axis. Step two, we'll then draw a horizontal line, draw the scale on the line, depending on what we decide to go by. We might go by ones. We just might start at 7 and go to 14 or something like that, you know? Then step 3, we're going to plot each data value above the line. If the value occurs more than once, we'll plot the others above the first point as well, kind of growing the stack of points. So in example 12, we're going to talk about teacher strikes. So in Pennsylvania, the number of teacher strikes for the last 14 years are shown, and we're going to construct a dot plot for this data. So we see all of our data, so we want to identify the lowest and highest values. So I see that the lowest is 3, and it looks like 15 is, oh, nope, looks like 18 is the highest. So now we want to kind of determine what our scale wants to be. So I tell you what, since 3 and 18, we'll just go by ones and just start at 0 all the way to 20. In reality, you could have probably started at 3 and gone to 18, but they did add the zeros to 20 as well. And then from there, we just plot it so they can see, all right, so I have a 3. So you would put a dot at 3, cross it out. They have a 9. Cross it out. They have a 13. Cross it out, a 15. Cross it out, 7. Another 7. So we'll stack it on top, 14. Another 9. So again, stacking, 10. 14, again, stacking. Another 7. So again, stacking that one. And then 2 8s, again, stacking them right on top of each other. Again, crossing them out as you go through it will let you know that you've done it. I've completely forgot my 18 over here because, again, it wasn't crossed out. But there you go. So it's, in a sense, it's just like another bar chart, just using dots instead of vertical bars. All right. So in the next section, or the last section we're going to talk about, is stem and leaf plots. So the fourth objective here is, again, to draw and interpret a stem and leaf plot. So a data plot that uses part of the data values as the stem, or the leftmost digit or digits, and part of the data as the leaf, usually the last digit, to form groups or classes. The plot shows the shape of the data while preserving the details. So step 1, we'll arrange the data in order. Step 2, separate the data according to the first digit. Step 3, construct the display by using the leading digit as the stem and the trailing digit as the leaf. So let's look at that. So in example 13, we're looking at an outpatient cardiogram. So at an outpatient testing center, the number of cardiograms performed each day for 20 days is shown. We're going to construct a stem and leaf plot for the data. So again, we're going to arrange the data in order. So they went from, again, from 0 to all the way to 57, least to greatest. Note, arranging the data in order is not essential and can be cumbersome when the data is large. However, it is helpful to construct a stem and leaf plot, and the leaves is the final stem, and the leaf plot should be arranged in order. I'm honestly going to be honest with you. I don't usually put it in least to greatest. I almost treat this just like a dot plot. And what I'll actually do is I'll pay attention to what I'm going to let be my stem. I see that these are all 2-digit numbers. So the tens place would represent my digit stem. And I see I have a 0, and I see, looks like 5. I'll identify the smallest and largest for sure. So I see 0, 2, and 57 are my smallest and largest. So I'll make stems of 0, 1, 2, 3, 4, 5. And then I'll just go in order. All right, 25, so I'll put a 5. So I'll show you what that means. I know here they already have the numbers for you, but again, I would identify that 0 to 5 was my stem. So again, I would have wrote 0, 1, 2, 3, 4, 5. And then as I went through this, again, not least to greatest, I would have said, all right, 25. So I'd have put a 2 and a 5. Again, leaving some space because it does have to be from least to greatest on the final product. Then I would have saw 3 and 1, so I've done 3 and then a 1. I would have saw 20, so I would have done 2 and 0, putting the 0 in front of the 5. A 3 and a 2, so I would put a 2 there. A 1 and a 3. A 1 and a 4. 4 and a 3. The 0 and the 2. The 5 and the 7. The 2 and the 3, putting the 3 between the 0 and 5, again, keeping it from least to greatest. 3, then 6, 3, then 2. So putting that 6 kind of way out there so I can figure out all the numbers that need to go in between. A 33 right there, and then another 32. So putting maybe I erased the 3, put the 2 there, kind of put that in order that way. Then 44, so I have a 4 down. 32, so again, maybe erasing a little bit more, putting the 2 there. 52, 44, then 51. So putting that 1 in front of the 2 and the 7, and then finishing it with a 45. So again, it does help if it is from least to greatest, but a lot of times you have a very large set of data. So sometimes just putting it in least to greatest as you produce the stem and leaf plot can be just as easy, so you're not having to do twice the work to produce the same thing. All right, so let's produce one of our own that's not already done for us. In example 14, we're going to look at calories per 1 ounce of salad dressing. So it says a listing of calories per 1 ounce of selected salad dressing, not fat-free, as if it matters, is given below. Construct a stem and leaf plot for the data. All right, so we're going to arrange the data in order. So let's work on that. Least to greatest. So these are all 3-digit numbers. So I think 100 would have to be the smallest one. There's a second 100. There's another one. There's another one. There's another one. All right, I see 130. I wonder if there is. There's a 110. A 110. All right, I saw 115 earlier. Oh, there it is right there, 115. Okay, so the next one should be a 120. There's a 120 right there. There's a 120 right there. A 120 right there. A 120 right there. 120. 120. And then I didn't see any 25, so I'm gonna go to 130. There's another 130. There's another 130. Another 130. Another 130. Okay, let's go to 140. Another 140. Another 140. Another 140. I remember seeing a 145. And there's 3 of them. So 145, 145, 145. And I think that's it. So then 150. There's one right there. There it is right there. All right, then 160. There's one here. One here. There's another one right there. Another one. And another one. There's a 170. It looks like I only have two 180s left. All right, make sure I got a number all crossed out. Make sure I didn't lose any or forget any. So there's my numbers arranged in order. Step 2, now determine the stems, the leading 2 digits of each number for the 3-digit numbers, and the leaves will be the last digit of the number. So again, I go from 100 to 180. So that means I'm basically going to go from 10 to 18. All right, there you go. So now we're ready to construct our stem and leaf plots. Just gonna try to keep my data where I can see it. So that when I erase this, I can still have it since y'all already have it on y'all's page. All right, I just don't like that. I'm gonna try to squeeze it all on this first one. So there we go. So then this would be 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, so then with 10, I had 1, 2, 3, 4, 5, 100s. So that's going to be 1, 2, 3, 4, 5. 110 had 2. So that'd be 1, 2. But then I had 115. So that's going to be a 5. So there you go right there. My 12 or 120, I had 1, 2, 3, 4, 5, 6. So that would be 6 zeros. So 1, 2, 3, 4, 5, 6. Try to keep them lined up to show the correct ratio. 130s, I had 1, 2, 3, 4, 5 of them. So that would be 1, 2, 3, 4, 5. 140, I had 1, 2, 3, 4 of them. So that'd be 1, 2, 3, 4. But then I also had 3 145s. So that'd be 1, 2, 3. I had 1, 2 150s. So there's 2 zeros there. I had 1, 2, 3, 4, 5 160s. So 1, 2, 3, 4, 5. 17, I had 1. 18, I had 2. So there's my stem and leaf. So then using that data, let's answer this question here. So we look for peaks and gaps in the distribution. Is the distribution symmetric? Is it skewed? What does the graph show about the variability of what we're seeing? And you can kind of illustrate that it looks like it peaks at the 140 marks. So peaks at the 140s, mainly since it had like 7 numbers, right? 1, 2, 3, 4, 5, 6, 7 numbers. That was the largest. You could also argue as well that maybe there was a second peak at 120 since it had 6 numbers. It doesn't seem that it's very symmetric, so not symmetric. And in reality, it also doesn't look very skewed either. So I don't see anything going more left or right since the data is kind of set there in the middle. So I'm going to go with not skewed. Because there's 2 pretty big peaks, I would say this is a multimodal. So again, a multimodal, since there were 2 peaks, not next to each other. And then I would argue too that the data seems pretty scattered. There's not just one focus point. So the data seems scattered. All right, so back-to-back stem and leaf plots is what we're going to look at next. It's basically just two stems and leaf plots used to compare pretty much similar data or two data sets so that the leaves for one set of the data are on the same side, are on one side of the stem, and the leaves for the other are on the other side. So they share the same stem, they just have leaves on both the left and the right, depending on what data you're looking at. And then each set of the leaves are arranged in, again, numerical order from the stem. All right, so let's look at a back-to-back stem leaf plot. Oh, man, almost had it. All right, so in example 15, we're going to look at the number of stories in tall buildings. So it says the number of stories in two selected samples of tall buildings in Atlanta and Philadelphia is shown. We're going to construct a back-to-back stem and leaf plot and compare the distribution. So you can see all the different stories in Atlanta's building, all of the buildings in Philadelphia, and the amount of stories they have. Again, arrange the data from least to greatest, both for Atlanta and Philadelphia. So for Atlanta, it would go from 26 through 70. The range of the data for Philadelphia goes from 25 through 61. So what we'll do is we'll argue that the stems probably need to be 2 through 6, since the 20s is the smallest number, and not 2 through 7, since 70 was the largest number on the other side. So once the data is ordered, we're going to arrange each data set in order from the smallest to the largest from the stem out. In this case, the Atlanta data will be on the left side. So the smaller values are right justified next to the stems, and the Philadelphia data, which is on the right, is left justified next to the stems. Meaning, when you're reading the Atlanta data, you're going to read it from the left to the right, or sorry, from the right to the left. So this would be 26, 28, 29. This is 31, 32, 32. Where Philadelphia, you can still read it from left to right. So 25, 30, 30, 30, 30, 32, and so on and so on. Right? And this is basically what a stem and leaf back to back would look like. And you can kind of analyze that. You can look at both sets of the data. You can just talk about Atlanta's and then independently talk about Philadelphia's. Maybe you want to compare a little bit more. You could argue that Atlanta is, again, another multimodal, so it looks like it peaks at 3 and has a little bit slight of a peak at 5, versus Philadelphia has one single peak. And then all the data is kind of on the left side. So it'd be a right skew. So the other data is kind of pulling from the left side. So you could argue things like that. So with that, we're going to go into what we call misleading graphs. Again, this is what you see mostly on any type of news or any product that people are trying to sell you. So graphs are a visual representation enabling readers to analyze and interpret data more easily than they could by looking at the numbers. Inappropriately drawn graphs can misrepresent the data and guide readers to incorrect conclusions. And I talked about this when talking about pie charts and even the bar graphs, depending on where the axis starts and goes by. This scale, again, it talks about the scale of the vertical axis should not be truncated unless the reader is made aware of the change. So we have to focus on stuff like that. So what we're going to do is we're going to look at example 16 here. Talking about changing the scale of a vertical axis to magnify the differences. And we saw this with the prices of the fast food joints. So here you can see if we use scale from 95 to 100, it definitely looks like manufacturer automobiles is really like almost double the amount of competitor two's automobiles, versus if you actually use 0 to 100, it's barely noticeable difference there. So you want to again pay attention to the axis. The manufacturer automobiles is at 98, but competitor 2 is only at 96. There's only a 2% difference, but that 2% difference that it looks like it is double the amount. So again, if I am the manufacturer automobile, I'm going to put the one on the left to make you think I'm just that much better than the other two competitors. If I'm the competitors, I know my stuff isn't as good. I'm with the one on the right to say we're all about the same. We just have maybe cheaper prices or something, just come to ours, whatever the case might be. Let's look at example 7 now. Changing the scale on the vertical axis for a line graph, or in this case, this would be a time series graph. So you can see if I go 0 to 25, going by fives from 2002 to 2011, it doesn't look like it moves at all. It looks like it goes to about 22 to about 23 or so. But then if you look at the one on the right, now it's starting at 21, going by ones. So now it looks like it has really increased from 2008 to 2011. But again, if you pay attention to the numbers, it really, again, only went from 22 to 23 miles per gallon when looking at, I guess, the projected miles per gallons for a car, right? So again, we can always skew our charts to, it's all, both of these charts, by the way, are truthful. These are facts that are written on a graph. It's just how it's represented can skew the mindset of the reader, which is a lot of times what we're trying to do if we're trying to sell something. But again, graphs should always be labeled on both the X and Y axis, so the magnitude of the differences is apparent to the reader. So again, as long as I'm labeling my stuff, I have not manipulated data. I just skewed it for someone that maybe doesn't pay attention to it. And that would be the hope there. One-dimensional increases or decreases should be illustrated using one-dimensional means instead of exaggerating the difference by using two-dimensional pictures. And you'll see here, so the difference shown with a one-dimensional graph and a two-dimensional graph. So here we have a typical bar graph using the same width, which is what I always talk about. And in 2012 versus 1967, Super Bowl commercials, the cost of it going from, I can't even tell you, it looks like maybe $100,000 to $3.5 million. That right there on the left should be how it should be presented. The one on the right, though, using objects or other shapes can be misleading as well, because it still goes to the 3.5 and it still goes to maybe 0.1. I guess that'll be the argument there. But the width of the shape should still be the same. So again, the source for the information presented should be included so the reader can analyze or determine the reliability of the organization presenting the data. So in example 19, comparisons without any vertical scale. We have no idea. We look at this and we're like, all right, the North looks like it has the highest cost of living. Economic growth is better in the West. Population growth is better in the West. Crime rate is the worst in the West. But the issue is, since there's no scale on the left side, this could be talking about 10 to 20% more, and that would be dramatic. But this could be also 0.1 to 0.2% more, which wouldn't be much of a difference, but you won't know that because there's no vertical scale. So we want to make sure there's a vertical scale so the reader can look at the data accurately and go, okay, I see this one's just magnified, or maybe it's that big of a difference. But again, if I'm trying to sell the west or the north or the east or the south, whatever I'm trying to do, I can skew these type of charts to go, well, this is factual. We just took some information off that you don't know. All right, so in this last part right here, talking about paired data and scatter plots, our fifth objective, we're going to draw and interpret a scatter